Bayes' rule has a wide range of applications from medical decision-making to understanding the weight of evidence in legal trials, and in fact, any situation when evidence is used to infer something from observation. But sometimes tricky, or where Bayes' rule is a little harder to intuitively understand, is when the thing we want to infer is a priori very unlikely, like having a bad medical condition or being a criminal, which is a priori an unlikely conclusion to draw without evidence. So let's try to see an example of this form to understand what's going on better. So let's consider a very rare disease, a condition that 1 in every 10,000 people might have. And suppose you have a pretty good test for diagnosing this condition. It has a 1% error rate. To keep things simple, let's even assume that the error is 100% correct on people who have the condition, so it gets it 100% right all the time. Where it makes an error is that it has what's called a 1% false positive rate. That is diagnoses 99% of the people who don't have the condition correctly as not having it, but makes a 1% error out of every 100 people it expects to have one who tests positive by mistake. Another question we're asking, suppose a person is tested positive, what is the probability that he or she actually has the condition? So let's try to set this up as a Bayes rule. It's exactly right for this. The sample space is all people, so all the population is our sample space. One part of it is the set of people who have the condition. It's a very small part. Let's call this A. A is the people with the condition. I drew it as a bit bigger area than 1 in 10,000 because 1 in 10,000 would be literally not visible on the screen, but it's a small area. And then we're interested in the people who test positive. And testing positive came in 2 parts. All the people, according to our story, who have the condition correctly test positive. But the test also has an error rate. So some subset of people who actually are not, don't have the condition, are not sick, also test positive. 1% of them, and again, I drew it a bit bigger than 1% because 1% would not be so visible on the screen. So the people who test positive came from the group of people who actually have the condition and the group of people who don't have the condition, but they're part of the 1% error rate of the test. That's our set B. And what we're interested in is probability of A conditioned on B. Someone who tested positive, what's the probability that they have the disease? To use Bayes' rule, we need all kinds of probabilities. We need to know what's the probability of having the condition up front, which according to our story, it's 1 in 10,000, so 100% probability of having the condition not having seen the test. That's probability of A. We know probability of B conditioned on A. That's 1. We know that everyone who has the condition will test positive. And the last term we need is the probability of B. So remember, Bayes' rule said probability of A times probability of B conditioned on A divided by probability of B. So we still need probability of B. So what is the probability that someone has the condition? So B consisted of 2 parts, people who test positive because they have the condition, and people who don't have the condition, but the test made an error on them. And we can write this as probability of B is the probability of B conditioned on A times the probability of A. That's the part of people who have the condition, plus the probability of B conditioned on not A times the probability of not A. This is the part of the people who test positive even though they don't have the condition. And we have all these expressions, so we can evaluate all of it. The first term is they test positive for sure, and there's 1 in 10,000 of the probability that someone has the condition. And the second part, the test is 99% correct, so has only a 1% error rate, and it's 99.99% of the probability of the population does not have the condition. So the product of those 2 is the second term, the probability of the error. And then this gives us the probability of testing positive in the whole population, which we can work at to be about 1%. Now we are set with this, we can use Bayes' rule. So again, remember Bayes' rule, probability of A times the probability of B conditioned A divided by the probability of B. We have all these expressions, we can substitute, do the arithmetic, and come up with that the probability of A conditioned B is 1%. So what we learned that even after the patient tests positive, it's very unlikely that he or she has the condition, only 1% likely. So how come that we had such a great test and yet we can't do very good inference from it? What happened is that the condition was extremely rare, so rare that the 1% error rate sort of overwhelmed our test. If you test positive, the positive test is more likely to come from the 1% error than from having the condition, which is only 1 in 10,000. So pictorially, if I look at all the people who tested positive, a large chunk of that population, in fact, the overwhelming majority of that population, are the people who don't have the condition, but the test made a mistake. And only a very small segment of the population is ones that actually had the condition. Of course, the test did tell us something. Before doing the testing, you had a 1 in 10,000 probability of having the condition. After the test, this probability went up to 1 in 100. It made it more likely that the person has the condition, but it's still very unlikely. And what Bayes' rule allowed us to do is to have this compute exactly and know that the test, how much the test increased the probability that the person has the condition, and do correct inference.